In this video, we are working a homework problem. It's problem 7.1.510.xp in the Larson and Edwards Calculus Early Transcendental Functions textbook. It's in the section covering the area between two curves. It's an application problem. It says, concrete sections for a new building have the dimensions in meters and shape shown in the first figure below. And I've combined the first and second figure in the problem into this one figure, and we'll talk about that in a minute. To decrease the weight and aid in the hardening process, the concrete sections are often not completely solid. Complete the following to allow for cylindrical openings, such as those shown in the second figure. So I've drawn these all together on one figure. This is what's given to us. They superimpose an XY plane, on the figure. And in the XY plane, what you see is this region right here. This is the one face of this concrete section. And they tell us that it's 2 meters deep and that this curve is given by the equation y equals 1/3 times the square root of 5 minus x. To aid in our integration or antidifferentiation, I'm going to write that square root function as that expression to the 1/2 power. So that makes it a lot more obvious that I'm going to have to use a U-substitution in order to find the corresponding areas. So we've got that function here. We're shown that this ends up here at y equals 1. This function is equal to 0 when x equals 5, which makes sense. And then there's a 1/2 meter gap over here, or space here. And this is all one piece, and then this is solid all the way back. Now they also said that we are allowing for cylindrical openings, such as those shown in the figure. So what you're going to see when you look at one face of this concrete section is holes. You're going to see a hole here and a hole here and a hole here and a hole here. I don't know if you've ever bought furniture made out of particle board and it has those little holes in it that you're supposed to use when you put it together at home. This kind of looks like that. So you've got what looks like a circle on this face, but it goes all the way through here. Now, this problem involves finding the volume of this guy. So let's look at the first part. It says, find the area of the face of one section superimposed on the rectangular coordinate system, and then it asks us to round to 3 decimal places. Now, in order to do this, we're actually going to use a couple of shortcuts. Now this is going to be completely symmetric. My picture is not perfect, it's not symmetric yet, but I want this side, or I know that this side is, or that area is equal to that area. So what I can do if I want the area of the whole thing is I can just find the area of one side and I can multiply it by 2. This problem is in this section on the area between two curves, because if I want to find this area here, the area from x equals 0 to x equals 5, this area, I'm just going to use my formula for the area between two curves. Now I also have to account for this area, and then I have to subtract the area of each of these circles. So we'll have this area plus this area minus that area, and then we're going to take the whole thing and we're going to multiply by 2 to get the area of the entire face here. So that's the plan. I'm just going to do one side and then I'll multiply by 2 to get the other side. Okay, so on this side, over here, that first area, I'm just going to label that in red. The red area is the integral from 0 to 5 of the top function minus the bottom function. And the top function is y equals 1. And the bottom function is y equals 1/3 times the square root of 5 minus x, or for ease of integration, I'll write it that way. Make it easier to apply our antiderivative rules. And that's just the red area. If you want, you can call that area 1. So then I would evaluate this integral. The integral of 1 with respect to x is just x. We're evaluating that from 0 to 5. And then over here, that requires u sub. So I'm going to write that out separately. Still integrating from 0 to 5. And I need a U-substitution here. Notice I've got a composite function, a function nested inside another function. And if u is equal to 5 minus x, I can write everything here in terms of u. So u sub works. I think to use u sub because I see that function nested inside another function, I think. It's probably a u sub. So I let u equal 5 minus x. Then I compute du. That's -1 times dx. And then I multiply both sides. Well, I could multiply both sides by -1, but actually I don't need to, do I? I've got a -1 times dx up here. Okay. So next we want to write this integral entirely in terms of u. So the 1/3 times the integral of, this is u raised to the 1/2. And -1 dx is du. Now, in order for these to be equivalent or equal to each other, I need bounds for u. These are x values. This says integrate from x equals 0 to x equals 5. When I have a du over here, it has to say integrate from u equals some number to u equals a different number. To find those numbers, you just take the limits of integration from here and you substitute into your formula for u. So for my upper limit, when x equals 5, I get u equals 5 minus 5, which is 0. And for my lower limit, take the lower limit there and I plug it in. I get u equals 5 minus 0, which is 5. And don't forget you're adding this to this. Don't think that you're subtracting because that subtraction was taken care of by that negative dx. And that -1 times dx is a positive du. When I evaluate this function at 5 and 0 and subtract, I just get 5. Now, if you prefer, and a lot of students do prefer this, you might want to have that lower limit of equal to 0 and the upper limit equal to 5. So you might want to flip those. You can do that as long as you multiply by a -1 out front. Okay. Then I ask myself, do I have a basic rule for that? And I do. So we add 1 to the exponent. And then we divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. And you evaluate at u equals 0 and u equals 5 and subtract. At u equals 5, I have 5 to the 3/2 there. And I've got this over here. At u equals 0, I get 0. So I have that minus 0, which is 0. Okay. And anything to the 3/2 power is itself. So 5 times the square root of itself. And that's because this is 5 to the first times 5 to the 1/2. And when you add the exponents, you get 3/2. Okay, so that's the first area. I also need this area over here, which is easy enough to find. It's just length times width. The width here is 0.5, and the length is 1. So I'm going to call that area 2. So we have 0.5 meters squared. And I want to take those two areas, add them together, and then subtract the area of each of these little holes. Now, we'll say the smaller cylindrical opening is what they're calling it in the problem statement. For the smaller one, we're told that the diameter is 1/8 of a meter. And we know that the radius is 1/2 of the diameter. So I'll just take 1/2 of 1/8, which gives me 1/16. And that means the area of that little hole there, area of that little circle, we're subtracting, I'll call it area 3, is pi times the radius squared, which is pi times 1/16 squared. So that's for the smaller opening. Now we want to look at the larger opening. Doing the same thing that we did on the last one. The diameter is 1/4 of a meter. And again, that was given to us, it's in the figure. And we know that the radius is 1/2 of the diameter. So 1/2 times 1/4 is 1/8. You multiply straight across, and that fourth area is 1/2 times the radius squared, and the radius in this case is 1/8. Okay, so the total area of this side is area 1 plus area 2 minus the area of the small circle minus the area of the large circle. So the total area of the face is 2 times the area of one side. And the area of one side is our area 1 plus area 2 minus the area of the small circle minus the area of the large circle. And so we get 2 times 5 minus 2/9, times the 5 times the square root of 5. Of course, you could simplify that. That's actually that red area, area 1. And we're adding area 2, which is just 0.5. And we're subtracting the areas of those 2 circles. It's 1/16 squared. I don't know why I squared the pi, that's wrong. There we go. Pi r squared. Okay, so that's the total area. Now they asked us to find this to 3 decimal places. So I'm just going to enter that all in my calculator and round. So I've got, actually I'll do the expression in parentheses first and then I'll multiply by 2. So I have 5 minus 2 divided by, let me open parentheses, 2 divided by 9 times 5 times root 5. It's that first area. Plus 0.5 minus pi times 1/16 squared. Let's delete that. 1/16 squared, there we go. Minus another pi, shift and press that button on the Casio calculator. Pi is right there, sorry it's reflecting. Times 1/8 squared. That's half the area we're looking for, and we want to multiply by 2 to get the full area. And so we get 5.908 approximately. When I round to 3 decimal places, that's what I get, and that's meters squared. Now, the second part of the problem asks us to find the volume of the concrete in one of the sections. This is part B. It says by multiplying the area in part A by 2 meters. So obviously the answer to this is just this answer times 2. And again, let's look at our picture. It's because we're taking this area and we're multiplying it by that depth. So the volume is area times the depth. And so we've got 5.908 meters squared times 2 meters. Or you can use that exact answer from the last one, sorry about the reflection, times 2. And I'm rounding to 3 decimal places. That's approximately 11.816 meters cubed. Okay, and then part C says that 1 cubic meter of concrete weighs 5,000 pounds. For us to find the weight of the section. And this just reminds me of chemistry class. This is just dimensional analysis. If you've ever read The Martian, he does a bunch of dimensional analysis with potatoes, and you remember all that. So I've got this volume. And I'm trying to get to the appropriate weight. Well, I know that 1 cubic meter weighs 5,000 pounds. So I can use that ratio here to convert from cubic meters into pounds. I put the units that I'm trying to get rid of, which are the meters cubed in the denominator. 1 cubic meter is associated with 5,000 pounds. 1 cubic meter of concrete weighs this much. So when I multiply these guys, the units reduce and I get the weight. So I'll multiply by 5,000 and we're asked to round to the nearest whole number. Sorry about that reflection again. I get 59,082. Pretty heavy. And that's it. That's how we solved that problem.